if not already. Possibly now. All right, I think we're live. Something happened on my screen. Welcome, everyone. We're just going to wait a minute or two to make sure that we are fully live. Jamie and I are going to be talking about the central limit theorem today, and I'm very, very excited. Thank you for letting us know in the chat that you can see us. So I am very excited for this. Anyway, we are, I think, as usual, streaming on a couple of different services, but just as a reminder, we're going to be keeping an eye on the chat in YouTube. So if you are on Facebook or Twitch or one of the other platforms that we are streaming on, if you would like to code along with us and ask us questions or say hello, you can go to the YouTube streaming and let us know that you are here by saying hello in the chat. Cool. So I guess we can get started today. So I will share my screen. Today's lesson is going to be heavy on the theory. And we're definitely going to be doing some coding. Like we need some coding to get a sense of the theory, but the focus is going to be on understanding some pretty deep theoretical concepts, which I find super fun. But I think it can also be a little bit intimidating sometimes. So I really want to encourage everyone to ask questions if anything comes up that you are confused about. I really, really welcome questions because it will help me keep track of what is making sense to people and what's not, and we can slow down at any point and kind of recap things if anything is confusing. So again, as per usual, we're using some code that's available on our GitHub for this streaming series. If you want to download that code ahead of time, you're welcome to. There's also like a little simulated data set in here for this week's materials. So you can find that if you go to the GitHub page, and hopefully that is linked in YouTube and other streaming services. Cool. I'm going to open up starting code. Okay, so to get started, the first thing I want to prepare everyone for is I'm going to ask us to take on a couple of different personas during this lesson. So we're going to switch back and forth from the researcher perspective. So that's somebody who is trying to conduct some research, trying to analyze some data. We're going to switch between that and the all-powerful perspective. So we get in this lesson to be like gods or goddesses, whatever you want to call it. Or all powerful in some way, we get to like see things that the researcher would not get to see, and kind of imagine both perspectives. If we had all the knowledge that we could possibly have, and if we only had the knowledge that a researcher had. The other thing I want to kind of set up here is, up to this point, we have been talking through summary statistics, just basic descriptive statistics. We looked at some data visualizations as well. And so that content is really useful for a lot of different types of research that you might want to do. But I want to kind of separate what we're doing today from that a little bit and say, so you could kind of imagine two different types of questions that you want to answer. On the one side, you could imagine that, let's say you work at a company like Codecademy. There's, I think, like 150 employees at this point, And let's say you want to understand something about salary and demographic characteristics among employees, and you have the data for every single person that works at the company that you care about. Then you can just use descriptive statistics, because the thing that you care about, you have all of the data for. But there are a lot of situations where you cannot, for some reason, collect all of the data that you need to answer the question that you want to answer. And that could be for a variety of reasons. It could be just because the population that you care about is really large. Like, you want to understand trends between salary and demographics for all US adults. And you just cannot get that information for all US adults. That could be one situation. Another situation, a lot of times in like marketing, is that you can imagine you have a new feature for your product and you want to test it out and see if, or let's say like it's a different color subscribe button and you want to see if more people press the green subscribe button compared to the red subscribe button. And you want to know whether more people, like all the future visitors to your website, you want to know what all those people would do. But you can't see all the future people that will ever access your website. And in fact, even among the people that you do sample, you can't ever see what somebody would have done in another situation. So if you show someone a green button, you can't see what they would have done if they saw a red button. So that's another form of missing data. You just can't see, ideally you'd like to show every person that could possibly visit your website the red button, erase their memory, and then do the same thing with the green button and like see all of those things and then look at the data, but you can't always do that. So in that case, you need some other tools in order to understand something about a population, about all the people that might visit the website or feel confident about it, having only collected a smaller amount of data. Okay, I always do this. I ramble a little too much at the beginning of these. I hope I didn't lose too many people yet, but hopefully that sets up kind of the motivation for what we're doing. So what I have here is a Jupyter notebook. I'm just going to load a bunch of packages. I just copy this over every time I start a new project because I may not use all the packages, but at least I have all of them imported. And I can import more if I need. This hourly pay text file is, it's just essentially an array of numbers. And this was simulated, but what it's meant to represent is salaries in US dollars for theoretically all adult Americans. It's like, it's fake data, but it's based off of census data. So it's somewhat similar to what this would look like in real life. So I'm gonna go ahead and really quickly plot a histogram of this so we can take a look at it. Let's do like 100 bins and this. Maybe 100 was too many. Let's do 50. Okay. So it looks something like this, which we probably expect. There's this spike at kind of a low salary. It seems like most people are kind of, and this is hourly pay or hourly salary. So looks like most people are kind of under $20 an hour. There are some people between 20 and 40. And then it kind of drops off from there. There's some from 40 to 60, and then like very few, but still some people all the way up to $140 an hour in this chart. And you can see over here, this is like a pretty big scale. Each of these bars, this axis represents frequencies. So we have like frequencies for some of these bars of over 300,000. Cool. So this gives us a little bit of a sense. Right now we're in all powerful mode. So we're going to pretend in today's lesson, we're going to pretend that we're a researcher that's interested in figuring out what the average salary for all US adults is. And then as the all-powerful being, we can see data for salary information for all US adults. So those are the two perspectives we'll shift between. So right now we're all powerful. We can see this histogram and we can actually calculate the mean salary. So I'll do that. So if I do mean hourly pay, and actually I'll save this as mean salary and print it. Is this also big enough for everyone? I realize. Like, zoom in. And I can print the mean salary. Okay. So it's about $18.84. Cool. Okay, so we've taken a minute. We're all powerful. We know the answer to the question that our researcher is going to try to answer. We know that the average salary for all American adults based off of this, I don't know if this is exactly what it is. I think this data that I based this off of was from like 2013 or something, so it might be outdated, but it's approximately $18.84. We're going to pretend that that's the truth, that our researcher can't know. Now we're going to, for a minute, imagine that we are a researcher. So as this researcher, we are going to try to answer our question, what's the mean salary of US adults? And we're going to do that by finding a sample of US adults and calculating their mean salary, because that's all we can do, right? We can find, by sample, I mean like some subset of this original set of numbers, right? Some subset of all the people that we actually care about. Cool. So I'm going to actually, hold on, I'm going to open up the final code and pull this over so that I can also see it because I just want to make sure. Okay. There's a few different ways to do this, a few different functions that you can use for random sampling. I guess for this, at least in the final code I gave you guys, I used random, so I'll use that here. So I'm just going to demo really fast what this random sample function does before we do any examples here. So if I just had an array, I'm going to call it ARR, of a bunch of numbers like 1, 1, 2, 2, 3, 4, 5, 6, 6, 7, 8. Okay, I've got a bunch of numbers in this array. If I say give me a random sample of array, and I say give me a random sample of 5 numbers, let's say. Oh, I guess actually it requires a list. It gives me a sampling of the numbers in this array. So this first time I got 6, 6, 5, 1, 8. One of the questions you might be interested in, and actually I'll do this again. So here's 5 different numbers. Interesting that I got the 2 6s again. Oops, let's try it again. 2 6s again, wow. Okay, that time I only got 1. So it will run this randomly every single time, and we'll get different results every single time. One thing you might be interested in is whether there's replacement here. So by replacement, I mean after it picks a number, can that number be picked again? By default, this function does not use replacement, but if you wanted to, you could always do a quick Google search to try to figure that out. So I'm just going to demonstrate because this is also a coding demo. So actually, no, the function documentation. Nope. All right, let's try this again. This was a bad demo. random sample, Python. And we'll go back to all. Okay. It's weird that the function documentation doesn't come up right away, but here, I guess, is the whole random package. So it'll be in here somewhere. Do fine sample. Yeah, there it is. And you can look through and see what all of the parameters are. Should say somewhere whether it is replaceable. Oh yeah, sampling without replacement. So it's not going to put anything back. Okay. So we have this sample from our array, and we can see that we can do this in Python. So now I'm going to demo this using our full population. So I'm imagining I'm the researcher, and I'm going to go in, and as the researcher, I'm going to find a sample or a subset of people in this population, and I'm going to collect their salaries. So let's do it this way. I'm going to call this samp1. And I'm going to pass in, what did we call it? Hourly pay. Actually, okay. Just to make everything super, super clear, I'm going to say, I'm going to resave this as something called population. I'm going to save it as a list. But I'm just saving the exact same numbers again, so that we're really clear that this is the full population, and then this is going to be our sample. So we'll sample from that population, and I don't know, Jamie, pick a number. How many do we want to sample from it?
20.
Okay, let's sample 20 people to start. And then let's print out the mean of our sample. And it was 17.24. Interesting. Okay. We could do this as many times as we wanted. So if we do this again, because this is random sampling, we're going to get different samples every single time. So I'll do it again. We got something different. I also think, so I'll show you really quickly hist samp1. Okay, let's pick a slightly larger sample size. Let's do like 150 so we can really see it. If we look at this histogram, right, of a sample of 150 people from our population, you'll notice that it looks pretty similar to our original histogram that we made, right? Like, so our original one looked like this. There was a spike around 0. Then there was this long tail. Most of the density of this thing was between 0 and 20, then 20 to 40. And if we look back at this, we see kind of a similar shape, right? We've still got this low spike. We've got some high density between 0 to 20, some like medium density from 20 to 40, and we've got this kind of long tail. Obviously, it's a little bit sparser, but we see a similar shape, and we see that this mean for our sample, 18.65, is kind of pretty similar to the mean for the overall population. And no matter how many times we do this, taking different samples of 150 people from our population, which, let's see, how big is the population? Can I do len on this? Actually don't know. Yeah. Okay.
That's 3 million.
Well, I guess this is not the whole population because it's not as long as it would need to be, but you'll have to suspend disbelief. So we've got like 3 million in here. We can imagine that the population was something else. I don't know. Okay, so, but we do see, right, that no matter how many times we do this, we're going to get a sample that's somewhat similar to the population. It's not going to be exactly the same. It's going to be slightly different every time. There might be different outliers that show up. Like this one randomly has 2 people, I think, out in this like over 100 per hour category, which is kind of surprising given how rare that is in the full population. But sometimes just by random chance, we'll get those people. So, okay. And the framework that we're now going to take, so I'll do this one more time because it's kind of fun, is we're going to think about what happens if we do this a lot of times. So now that we have pretended to be the researcher, we've taken a sample from our population, we have taken a look at it and seen that it's similar to the population, but there's some variation in there. Sometimes we get a high mean, sometimes we get a low mean compared to the population mean. Now we're going to go back to all powerful mode. Okay. So in our all powerful mode, what we're going to do is we're going to repeat this process a whole bunch of times. So Jamie, what kind of coding technique do you think I should use to repeat this a bunch of times? Or what, do you have any ideas how I could kind of go about that?
Yeah. So I guess if we want to basically repeat the same process a lot of times, we might maybe want to use some type of loop to like have it automatically do it.
Yeah. Yeah, so instead of just pressing this run button a bunch of times and seeing what the output is, I'm going to use a for loop. And I could use a different kind of loop, actually. There's nothing, I could use like a while loop as well. But I'm just going to use a for loop because it's easy. And what I'm going to do is I'm going to say for I in range, I don't know, like 10,000. What this is going to do is it's going to repeat the process that I tell Python to repeat. It's going to repeat it 10,000 times. It might seem a little bit silly that I have this like I here, where I say for I in range 10,000. I'm not going to use it for the purposes of what we're doing here. I'm really just setting this up because I just want something to happen 10,000 times. I want to kind of like, essentially, if I was coding something else, right, every time this, whatever code I put down here under the for loop would happen, every time that would happen, I would increase by 1 and it would start at 0. So go 0, 1, 2, 3, 4. Right. So like if I print for I in range 10, print I, and I run this, I'm just going to get the numbers 0 through 9 because I is going to be 0 the first time, then it's going to be 1, then it's going to be 2, and it's going to happen 10 times in total, and it's going to print out the value of I each time. But I'm just not going to use I because I don't need it. I just need something to happen 10,000 times or a large number of times. Okay. Actually, good coding practice is to never start a loop by repeating something 10,000 times, because if you screw up the code, then it can get stuck and like quit out on you. So I like to start with like 10 and then we'll iterate on this. So I'm going to kind of grab my code from up here. I've got population has already been saved. And every time in this loop, what I'm going to do is take a sample, call it sample, of some number of observations. And then I'm going to calculate the mean of the sample. Actually, I'm going to call this samp because another good coding practice is to not name variables the same thing as functions, because that can sometimes get a little bit mixed up. Great. Okay, so I'm going to calculate the mean of SAMP, but I don't want to just calculate the mean and just let it go. I want to save it somewhere. So Jamie, do you have any ideas for how I could save it?
Yeah, so we're probably going to want to save more than one of these because we're going to be iterating a lot. So we could save it inside of a list.
Cool.
So maybe we can make like a list outside of the for loop that
I'll
is
call it,
empty, that we can just add stuff to it.
Yeah. So I'm going to create an empty list called SAMP means. Perfect. And then I'm going to say SAMP means dot append, which means append that value onto the list. And I'm going to append the mean of that particular sample. So, okay. And now I'm just going to print out what this looks like after 10 iterations. And we'll take a look at it. Cool. So all of what we've done here is we've taken 10 different samples of 150 each. For each sample, we calculated the mean and we saved that in our list. So the first sample mean was 20.68. This next one was 19.35, then 18.66, and so on and so forth. I saw that there was a question about memorizing and knowing how the number goes. So yes, I think Jamie responded, but if you could clarify that question, I would be happy to answer it. Okay. So, all right, so we've done this. We've confirmed that we can do it 10 times and we can collect 10 sample means. And now I'm going to do it a whole bunch more times. I'm going to do 10,000. I'm going to run it. I'm not going to print it anymore because that's going to be 10,000 numbers. But what I will do is I will make a histogram of it. This will take a second to run. Cool. Interesting. Okay, so let's break down what this picture is telling us. So remember that what we did as all-powerful beings is that we collected 10,000 different samples. Each sample had 150 people in it. For each sample, we calculated the mean, and then we plotted a histogram of them. When we plotted this histogram, we saw that it looks kind of symmetrical. Part of the reason why I chose this data is because I think this is really a stark contrast to the population distribution, which I think is interesting. So like this population distribution, I would describe as very right skewed, right? There's this very, very long right-handed tail. And most of the data is on the low end of the distribution. But here, and that's true, right? For all of the individual samples that we took, all of those individual samples are also right skewed. But suddenly when we calculate sample means and we plot a histogram of all of the sample means, we get this really nice symmetrical distribution. And if we calculate the mean of all of the sample means, it's going to be, so it's like 18.82 about, which is almost exactly the same as the true population mean. And maybe that feels, I don't know, to me that feels like it makes sense that the mean of the means, like the middle of the means of all of these samples is going to be equal to the population mean. But it's actually like a super, super powerful statistical theorem that is not, I mean, we take it for granted, like what this means in like and I don't mean to use mathy terms, but there's this is called a unbiased estimator. So the mean is called an unbiased estimator of the population mean, which means that if you take a bunch of samples from a population and you calculate the mean for each one, on average, those sample means will be the same as the population mean. But that's not necessarily true for example, if you calculate standard deviation or variance of a population, it's almost an unbiased estimator, but that's why there's a difference. I don't know, some of you may have seen this, that there's a difference between calculating population standard deviation and sample standard deviation. You divide by n in one case and you divide by n minus 1 in the other case. And the reason for that is that if you divide by n, it becomes a ever so slightly biased estimator of the population standard deviation. And if you think of something like the maximum of a data set, which is another statistic that we might use. So like we might calculate the maximum salary in each sample. Like that might be something that we're interested in. If we take the maximum of all of these population or all of these samples and plot a histogram of the maximums, it's not going to be centered at the population maximum. So it's not true for all statistics that this lines up, but for the sample mean, it does, and it's really, really nice that it does. Okay, so I guess the first question is, why is this so valuable? And the reason it's so valuable is that it allows us to understand uncertainty. And uncertainty is really the key to statistics and inferential statistics specifically. Because again, put yourself in the feet of, or in the shoes of a researcher. Again, I like that marketing example. If you're you're trying to figure out what proportion of visitors to a website will press my green subscribe button, and you can only sample 1,000 people. You can only show the button to 1,000 people and observe what they do. You need to know how certain, let's say you find that 10% more people push the button if it's green than in the old version. You need to know how certain you can be that it's really 10% and not -1%, right? Like maybe in the population, it's -1%, but you just found in your random sample 10% more press that button. And in this case, right, like if you find as the researcher that the average salary is $16 an hour, you want to know how certain you can be that that lines up with the population average salary, if that's what you're trying to estimate. You want to know how far off you could be. And that's what this tells you. It tells you how far off you could possibly be, because it gives you a sense of how spread out these numbers and how spread out the sample means are. If you were all powerful and you could take a bunch of sample means of that size, this tells you how spread out they could possibly be. So I guess one of the things that I'll point out here, and maybe we intuit it, but I think it's like a powerful thing to show, is what happens when we change the sample size. So what I'm going to do is I'm going to make sure that we plot this on the same axis every time. I'm going to set plt.xlim of 0 to 40. And I'll plot this again. Whoop. Yeah. Okay, so I'm just plotting this from 0 to 40 so we can see the full thing. If I do this again with, let's say, a sample size of 100 instead, it's going to be a little bit wider. Let's pick something lower, really show it. Gonna sample size of 50. Okay, so now we can see, right, this distribution, when we took samples of size 50, it's going from, the sample means are going from 10 all the way up to 30. Here, they're going between like 15 and 25, which makes some sense, right? Because if you think about it, if you take a bigger sample, it's more likely to be representative of the population than if you take a small sample, then you could have outliers that throw everything off. The other thing that I won't demo here, but the other thing that can influence this, the width of this thing, is the amount of variation in the population. So if the population has a lot of variation, the width of this thing will be bigger. And if the population has very little variation, like let's say everybody's salary was around $20 instead of that spread out distribution that we saw before going all the way up to 140, then there's just going to be less variation in sample means by default, right? Like if everybody was making $20 in the most extreme case, then all of the sample means would be exactly 20. So however much variation there is in the population will also influence this. So what I'll show, I think like a cool thing to see just to kind of verify it even, is that, and this is the official central limit theorem that we're getting to now, is that we can basically describe exactly what this shape is going to look like mathematically without having done what we did here, which is take all of these sample means. I'm going to plot this again, but this time I'm going to grab some kind of, this is again, like a little bit, I don't mean to just like pull fancy code and make everybody accept it. But I'll talk through what this is doing. So on top of this histogram, what I'm going to do, and I'm going to normalize the histogram, which means, or actually, I'm going to switch to a dist plot. What I'm doing here is I'm normalizing the histogram. So here, the histogram is going from 0 to 600 on the y-axis. These are frequencies. And if I were to say density equals true here, or if I use dist plot, and I'll demo that in a second, all that does is it changes this y-axis so that the scale of this is such that the total area of this thing adds up to 1. This is so that it mimics what's called a probability distribution function, which you don't really need to know too much about right now, but that allows us to compare this to kind of mathematical functions. And if we do dist plot here, it does the exact same thing. It also puts what's called a, whoops. Oh yeah, it doesn't take bins. It also, oh, it's SNS. My bad. It also gives you this kernel density estimation. Again, not super important. All you need to know is it's kind of like a smoothed version of this histogram. So it's trying to like smooth out this, this shape. So if we do this, okay, what I've done, I'm going to walk through what this code is doing. Or maybe Jamie, do you want to try to walk through what this code is doing? I'm putting you on the spot a little bit.
Yeah, sure. Okay.
Let me just change some things. Okay.
Okay. So where should I start from? Should I start from mu and sigma, or?
So I guess mu is just the population mean. I'll come back to this in a second. So maybe start with this. What does this linspace thing do?
Linspace. So linspace mu minus 3 times sigma. Oh, so I think linspace, you're basically setting up like an interval range using mu and sigma which I think Sophie said she'll come back and explain what sigma is. But basically, it's going to set a range of values in a variable called x. And then you're going to plot that range of values. And then what is stats.norm.pdf? I think that's just like to like give a normal distribution with the given x and with the given range of values mu and sigma.
So I'll demo this part really fast. Actually, I should have done just like 10 numbers. All that linspace does is it says, okay, start at 0, end at 1, and give me 10 numbers that are equally spaced. So this just gives me 10 numbers between 0 and 1 that are equally spaced apart. And all I'm doing here is I'm saying, basically, this is something that is not super important, but this gives me a sense of how wide the x-axis of my distribution is going to be. Basically, I'm just saying, like, what's the lowest number I need to plot here? What's the highest number I need to plot here in order to fit this on my graph? And I'm getting 100 numbers. And then I'm going to get essentially the normal distribution version of this. A normal distribution, again, is a probability distribution. And all you need to know for right now is that it describes a particular shape of this distribution mathematically. And so I'm plugging in all of those values that I just got between the two ends of that distribution, calculating how high that line needs to be. And I'm just using them to draw that line on top of my graph. And when I do that, oh, it's because I did this again. Did I not save this? Sorry, guys. Oh. SciPy, import stats. Okay. Gonna run. Okay, there we go. So what you see here is I've drawn in black what's called the normal distribution on top of the distribution that we got just by taking samples of size 50 and plotting the and collecting the means for each sample. And what you see here is that it's basically the same thing. So I've used like a mathematical formula to say what the shape should look like. And then we've kind of proven what that shape actually looks like by taking the samples. And what I've done here is I've drawn a normal distribution that has a mean that's equal to the population mean and a standard deviation that's equal to the population standard deviation divided by the square root of the sample size. That's what this double time sign means to 0.5. So taking something to the 0.5 power is the same as taking the square root of it. So 50 times 0.5 is the square root of 50. And then, so this whole thing is standard deviation of the population divided by the square root of the sample size. And we see it that if we take a normal distribution with those parameters, again, mathematical description of a curve, it really perfectly matches up with what this shape looks like. And this piece, the standard deviation of the population divided by the square root of the sample size, this is what's called the standard error of the mean.
So Sophie, we have a question from the chat, which is asking like, which part of the code you made was like the actual normal distribution? Was the actual normal distribution?
Perfect. I should have commented this out. So this part here, I'm just plotting the sample means. This part here is where I'm plotting the normal distribution on top of it. Great. Awesome. So yeah, I think I mean, we're going to run out of time for all of the things I want to cover today, but I do think like just taking a second to stop and look at this picture makes me just really happy. It's really, really beautiful because statisticians have like, it seems like almost magically figured out these crazy formulas to describe things that seem, I don't know, hard to describe. And it's really cool that we can quantify our uncertainty in this way. Okay, so again, coming back to the standard error piece. So the standard error, again, is the standard deviation of this sampling distribution. It's basically a measure of how wide is the sampling distribution, and the sampling distribution, again, because I feel like no matter how many times I heard this when I was first learning it, it like took maybe 100 times of hearing this before it clicked in my brain. The sampling distribution we got from taking samples of the same size, calculating the mean for each one, and then plotting the distribution of the means. The standard error is a description of how wide that distribution is. Okay. All right, so we've made it pretty far. We've gotten some interesting things already out on the table. Now, so we were in all powerful mode. We made this distribution. We saw what it looked like. We proved to ourselves that the central limit theorem works. I don't even think I said what the central limit theorem is, but we just proved it basically without even using any math, which is super cool. The central limit theorem just says that this distribution is normal and that the mean normally distributed, so it follows this shape. The mean is the same as the population mean, and the standard deviation is equal to the population standard deviation divided by the square root of the sample size. That's the whole central limit theorem. You could do it with math, or you could do it by actually taking all those samples and calculating the mean of each one. Okay, so now let's go back for a moment to the perspective of the researcher. So like, all right, back in researcher mode. Woo! I should have put these in the final code, would have been helpful. Okay, so we're back in researcher mode, and now we're not all powerful anymore. We can't actually see what this distribution, or we can't actually see the whole population, so we can't take samples from the whole population and see what the distribution looks like. But now that we have the central limit theorem, we actually kind of can see what it looks like, or we can approximate what it looks like. So remember the things that we needed to plot that black line. So to plot the blue histogram, we needed to take samples from the full population. But to get the black line, all we needed to know was the mean of the population and the standard deviation of the population and the sample size. Other than that, we didn't need any more information. So we can approximate this if we have an estimate of the population mean and of the standard deviation of the population, and we're going to get those things from our sample. They're not going to be perfect. We don't know what the population mean is anyway. We're trying to estimate it. The sample standard deviation, like I said, it's going to be an unbiased estimator of the population mean if we calculate it with that n-1 on the denominator, which we will. But it's not going to be perfect. We can still do it though. So let's go back. I'm again going to print the mean for our sample. I think we still have a sample one somewhere in our, or what did I call it? Let's see. Yeah, we called it sample one. We still have a sample in here somewhere. Let's like calculate a new one. Ooh, that was a good one. It was low. Okay. Okay, so we have a sample. Let's calculate also the standard deviation of that sample. And I'm going to save those things. Sample mean equals and sample standard deviation, and we'll print them. And we see, okay, so the sample mean is equal to 16.33. The population, or sorry, the sample standard deviation was 13.21. Okay, all powerful mode for a second. Let's remind ourselves of what these values are for the population. So print v dot mean of population, and also for standard deviation. Okay. So what we notice here is that our sample that we took had less variation than the population. So the sample standard deviation was 13.2. The population standard deviation was 18.1. So we're going to underestimate the amount of variation in this sample. The larger the sample we take, the better of an approximation we're going to get here. But we're going to work with it because it gives us at least some sense. Back to researcher mode. So as the researcher, we're now going to estimate what this distribution looks like. So I'm actually going to grab this exact same code, but now we're going to do this with the just the information from the sample. So we have our sample mean, we have our sample standard deviation. We're going to use a mu, which is really just the mean of this normal distribution of the sample mean. And we're going to use the sample standard deviation here. And I believe that sample was a size 150, but we'll just do len sample 1. That will tell us how many values are in there. Or even, I think, even clearer is to say sample size equals that. So we're really clear. And then we'll put sample size in this equation. And if we plot this, we get this curve. It's going to be, I should maybe plot it on top of this. So it's going to be more, or actually maybe less spread out than this. It's going to be a little bit off from what it should be. Ooh, that's more off than I thought it would be. Or it's smaller. Oh, it's because this was a sample size of 50. Sorry, ignore that. Let's redo this, I guess, with a sample size of 150. I know we're going to run out of time, but now this will. Right, so this is our estimation of this is a little bit off, pretty much because this estimate was so off. But what we can do is now use this distribution to try to estimate the plausible range of what values we might get if we could observe the entire population and take samples from it. So the reason why these two distributions are offset from each other is because this one we centered at the population, or the sample standard deviation. This one we centered at the population standard, sorry, at the sample mean for this one, at the population mean for this one. So they're off from that. But the width of it is the part that we really care about. And even though we were pretty far off on our sample standard deviation compared to the population standard deviation, the width of this distribution is pretty close to the width of what we would find if we were able to like be all powerful and see and take samples from everybody. And so what we end up doing is we end up using this distribution here to figure out a plausible range that the population mean might be in. And so we end up saying that the population mean is somewhere between, like, we think 12 and 20 or whatever, like, these points are. And we can choose percentiles. So we could do like the second percentile and the 98th percentile to cut off kind of the tails of this. But that's really all that a 95% confidence interval is. And I can demo that super fast. I know we're running out of time. But I also know that this is a super complicated, super complicated process and like mind experiment. So I think it's nice if we kind of stop here and get like 3 more minutes to talk about it a little bit. So here we go. All I'm doing here is I'm trying to find like the 2.5th percentile and the 97.5th percentile of this black line. Oops, I meant to put sample 1 here. And did I save this as standard error? I saved it as sigma. So this goes from roughly 14.22 to 18.45. And so if we were the researcher, we would say our sample mean was 16.33, but we are 95% confident that the true population mean is somewhere between 14.22 and 18.45, which is accurate, although it is really close to that upper bound, which was, a random fluke, and that happens. But this is the way that statisticians and data scientists use the central limit theorem to try to quantify their uncertainty about a sample mean without having been able to see the entire population. Cool. So I'm going to stop there. We've got 2 minutes to spare. Jamie, what do you think would be a good use of this time? Do you think there's anything that's worth like talking about? I hadn't had a good eye on the stream or on the chat. Were there any questions that came up?
I think we covered all the questions. Wait, one thing I'm curious about, what was the actual population mean? Because I'm wondering if it was actually within the 95%.
The population mean was 18.84, about 839. Okay. And so it was like just barely, yeah. But it wasn't in that range. Yeah. We could kind of do this with another sample. Like I wish I organized my code better, but it's organized better in the final version that is available on GitHub. But if I take another sample, here, let's find one that seems like similar to the population. Yeah, that seems more similar to the population. If we use a different sample where these things, yeah, so here, this one, we got a little bit closer in terms of standard error and mean, like our sample was more similar to the population. And then that will give us a slightly, a confidence interval that more comfortably includes the population mean. So again, like I think the thing that I had trouble conceptualizing for a really long time is that the central limit theorem tells us something about the shape of this black line, but it can't really tell us. We still have to make a leap there because we still don't know what the population standard deviation is. We still have to estimate the population standard deviation using our sample. And so it's not like totally magic that we can just recreate exactly this, but we can get a pretty good read on at least how much variation we can expect. And I think that is the true power. And I encourage, so there's on Codecademy, there is a article on the central limit theorem that kind of walks through this again. And so if you watch this series and you still feel a little confused, or you still want to like go back and confirm your understanding, I highly recommend that you read that article or look up on the internet central limit theorem and read about it, because I think this is one of those things. It's like, it's deceptively simple and also really deep. And I think even for me, I learned it about, like I said, like 100 times before I actually learned it. So, all right. Next week, we're going to jump into actually using this central limit theorem to run some hypothesis tests. And we're going to learn even more about how hypothesis tests work. So I'm really excited for that. But otherwise, thank you, Kevin, for that question. Kevin says, I have a question. Why are there only so few people watching? This is pure quality. Thank you. I agree. I don't know about quality, but I'm having a lot of fun doing these, and hopefully more people will find them after the fact. But for those that are here, you get the extra benefit of being able to ask questions and really speak with us personally. So please take advantage. All right. With that, I think we'll sign off. Everyone have a great rest of your Tuesday, and we hope that these are helpful. Goodbye.